Hey, what's up, Chem Peeps? What in the heck are we going to do in this vid? We are going to explain how systems at equilibrium respond to disturbances by partially countering the effect of the disturbance. As always, breaking it down. Uno, we are going to define LeChatelier's principle. Dos, we're going to use LeChatelier's principle to predict the direction of the shift resulting from various possible stresses on a system at chemical equilibrium. Alright, first, let's define what the heck LeChatelier's principle is. Let's define it. Basically, LeChatelier's principle just helps us figure out what's going to happen when we stress a system at equilibrium. It simply states that if a system is at equilibrium and it's disturbed, the position of equilibrium is going to shift to minimize that disturbance and reestablish equilibrium. And it's important to note that stressing the system will result in different concentrations or pressures of products and reactants, but the value of K will not change. That ratio of products to reactants is going to stay the same. All right, the first type of stress that we're going to talk about is adding or removing reactant or product from a system at equilibrium. Equilibrium system is going to shift away from the side with added chemicals and toward the side with removed chemicals. Again, our goal is to reestablish equilibrium. So, as you look at your notes, if you add more reactant, it's going to shift to form more product to reestablish that equilibrium ratio of products to reactants. Conversely, if the concentration of products is increased, the equilibrium is going to shift to form more reactants. Again, trying to reestablish that equilibrium ratio. So, take a look at the image that's on your screen and in your notes that shows you the equilibrium between N2O4 gas and NO2 gas. You're given original equilibrium conditions. Greater concentration of NO2 than N2O4. Illustrated here in our value of K. Notice what happens. We drop in a lot of N2O4. Notice in this graph that the addition is assumed to have happened instantaneously. Just boom, there it is. More reactant. So look at my value of Q and compare it to my value of K. Notice that K is greater than Q, because I dumped in a bunch of this reactant. And so my reaction is going to shift to form more product to reestablish equilibrium. Watch it, watch it. Boop. We shifted to form more product, used up some of our reactant to reestablish equilibrium. Notice how that appears in the graph. Form more product, use up some reactant, reestablish equilibrium. Or take a look at the other scenario. Now what we're going to do is dump in a bunch of product, NO2. Compare the value of K to Q. Boom! This time, Q is larger than K. So to reestablish equilibrium, our reaction is going to shift back to the reactant side. We're going to use up some of our product, form more of our reactant. Here we go. Boom! Reestablish equilibrium. Check it out on the graph. Using up some of our product, forming some of our reactant. Reestablishing equilibrium. Couple other things to note when we talk about LeChatelier's principle, adding or removing things. Commonly, you will be told that an inert gas is added to the mixture. But if it's inert, it's not going to react with anything in the equation, and therefore your equilibrium is going to remain unchanged. But you know College Board, always looking to trip you up. And second, look out for questions where you add something that's not part of the reaction but will affect it. So not something that's inert, but for example, really commonly, we could add, say, an acid that will react with a base, essentially using it up, removing it from the reaction. All right, so let's pause, take a moment to look at this animation. Here we have an equilibrium between an iron thiocyanate ion and the iron 3 and thiocyanate ion. Notice the coloration of the different ions. If I were to add a bunch of sodium thiocyanate, the focus being the thiocyanate ion, the sodium spectator in this equation, boop, add that thiocyanate, notice what happens here. The reaction is going to shift left. It's going to shift towards the reactant side, form more reactant, use up some of that product. Take a moment to again stare at our mixture. Notice that we formed more reactant, which has that characteristic red color, and so the color of our solution has become deeper red. Think about this same equilibrium reaction between iron thiocyanate ion and the iron 3 and thiocyanate ion. This time I'm going to remove some of that iron 3 ion. Boop. Notice what's going to happen here. The reaction will shift to the right to reestablish equilibrium. Again, notice what's happening with the color here. We've used up some of that red iron thiocyanate ion and formed more iron 3, causing a less red, more yellow color. All right, let's talk about another thing that stresses me out. People who don't watch videos, people who procrastinate, people who complain, people who don't do quests, people who don't take advantage of test corrections, people who don't come to tutorials. Let's talk about a second thing that stresses a system at equilibrium. Now, this one only applies to equilibrium systems involving gases. And in order to determine how the system is going to shift, to reestablish equilibrium, you need to count up the number of moles of gas, reactants, and gas products to predict what's going to happen. So let's take a look at an example. We've got nitrogen and hydrogen gas coming together to form ammonia gas. In this equilibrium example, we've got 4 moles of gas reactants, 1 mole of nitrogen gas, 3 moles of hydrogen gas, 2 moles of gas products, or 2 moles of ammonia. So how does volume or pressure stress a system? If the volume increases / pressure decreases, the system is going to shift to the side with a greater number of gas moles in order to increase the pressure and reestablish equilibrium. However, if the volume decreases or pressure increases, the system is going to shift to the side with fewer number of gas moles in order to decrease the pressure. Again, in both of these situations, you're trying to think about how is it going to shift to counteract that stress and reestablish equilibrium. Now there's a great image on your screen and in your notes. I encourage you to pause the video and stare at this image. It makes so much sense to me. Imagine we increase the pressure. They're gonna start banging around the walls, bing, bada, ding, bada, ding, bada, boom. And to reduce that pressure and reestablish equilibrium, it's gonna shift to the side where there are fewer moles of gas. There's less banging around on the sides. Conversely, if you decrease the pressure, it's gonna be less banging into the sides of the walls. Bing, bing, bing. So now it's gonna shift to the side that has more moles of gas so they can bang into the sides of the wall more often, increasing the pressure. Reestablishing equilibrium is sort of neutralizing that stress. All right, I've got another thriller of an animation to help you better visualize what's going on. We've got an equilibrium between diatomic iodine gas, illustrated using these purple particles, and iodine atoms, indicated here by these colorless iodine particles. If I increase the pressure, boop, decrease the volume, notice what happens to my equilibrium. Notice, some of our individual iodine atoms are coming together to form our diatomic iodine. The reaction is shifting to the side that has fewer moles of gas to reduce that stress of the added pressure or decreased volume. Conversely, if I decrease the pressure or increase the volume, watch what happens here in my equilibrium system. Notice now some of those iodine molecules break apart to form individual iodine atoms. The reaction shifts to the right, to the side that has a greater number of moles of product. Other things that stress me out. People who don't check the tutorial schedule on the website. People who don't rewatch videos for things they don't understand. People who push play and walk away. Third thing that will stress a system at equilibrium: temperature change. Easiest way to understand how temperature will affect or stress a system at equilibrium is to think of your heat energy as an additional reactant or product. And then just think of it as you did with adding or removing a reactant or product as we did earlier. So let's take a look at an exothermic reaction where energy will be a product. If you add energy to the system, it's going to shift in the reverse or endothermic direction. It's going to form more reactants. Again, you're putting heat energy in. If energy is taken away, the result is going to favor the formation of the forward or exothermic reaction. Again, giving that heat off. Exothermic. Conversely, with an endothermic reaction, your energy species would be on the reactant side. So here when you add energy, putting heat energy in, it's going to favor the endothermic or forward reaction. Conversely, removing that is going to favor the reverse or exothermic reaction, giving that heat energy off. All right, it's important to know that it's only temperature change that will result in a change in the value of your equilibrium constant. And this is a common trick question on the test. Changing pressure, changing volume, adding reactant, removing reactant, all of those things are going to shift the equilibrium, but the value of K is going to stay the same. Temperature change, on the other hand, will get you a new equilibrium constant value. All right, one more thriller of an animation. This time our focus is going to be on temperature. This animation mirrors the one that you've got in your notes, and note that it's an equilibrium between N2O4 and NO2 gas. Additionally, note that the N2O4 molecules are colorless and the NO2 molecules are brown. First, let's increase the temperature. Heating it up, Bunsen burner flame, cooking it, toasting it, it's lit. Notice this time that our N2O4 molecules are breaking apart to form more NO2. We shift right. In this endothermic reaction, as I add heat, the reaction is going to shift in the opposite direction. Notice how that added NO2 gives us a darker brown color. Now let's decrease the temperature. Putting some ice cubes around our beaker with our equilibrium mixture. Notice this time that our NO2 molecules are coming together to form more N2O4 or colorless species. This time we're removing heat, so the reaction is shifting left, essentially to make up for that reactant that was lost. Okay, now let's talk about how we're going to observe these shifts in equilibrium. Most commonly, we're going to look at color change. In reactions where reactants and products have different colors, the color of the equilibrium mixture can give you some important hints about the relative amount or proportions of reactants and products. Another common way to observe shifts in equilibrium is a change in pH. This is really common in reactions with hydrogen ions or hydroxide ions. You just measure the pH to monitor what the heck's going on with those shifts in equilibrium. All right, last couple of notes here focus on optimizing our yield. Chemists will often manipulate the conditions in order to form more products or reactants. It's a really important part of applying chemistry to industry. Let's take a look once again at the manufacture of ammonia. LeChatelier's principle predicts high pressures will produce more product, the side with fewer moles of gas. But high pressures can be really difficult to achieve. Also note that LeChatelier's principle predicts that low temperatures will produce more products. We've got an exothermic reaction, but low temperatures can mean slow reactions. So you have to sort of balance these two ideas in order to get some decent yields. We have to think about being cost effective, but also trying to make sure we can get the reaction to happen in a timely manner. And then just one final note here, recognize that catalysts do not affect the equilibrium position. They only affect the rate at which equilibrium is achieved. Again, common error on the AP test and something you definitely want to watch out for.